In this video, we're going to examine geometric optics, more specifically, Snell's Law. Now, recently, I've grown extremely fascinated by light or electromagnetic radiation, in particular, how it interacts with matter. For instance, as light goes from one material to another, if the second substance is more dense, it can actually impede the motion of the light. A portion of that light can pass through the second substance and bend or refract, whereas the remaining portion of light gets reflected. And I find this to be extremely fascinating. So here's N1. This represents the index of refraction of air. And this is N2. In this case, this equals 1.50, which is the index of refraction for glass. So this represents the capacity for glass to slow down or impede the motion of the light. Again, notice how the glass has a higher index of refraction. It's a more dense substance that can slow the light down. Suppose the light ray has an angle of 30 degrees in substance 1, which is air. We wish to find the angle of the light in substance 2. So we use the equation for Snell's law, N1 sine theta 1 equals N2 sine theta 2. I'll just plug in the numbers. Air, the angle in air, index of refraction for glass, sine of 30 is 0.5. 0.5 times 1 is itself. Divide both sides by 1.50. Take the inverse sine of both sides to isolate theta 2. (19.5 degrees is approximately theta 2. Notice how when you go from a material of a small index of refraction to a higher index of refraction, your angle decreases. So the light bends closer toward the axis, the vertical axis. You'll see what I mean in just a moment. Next, I'd like to show you how to calculate the intensity or the brightness of our light. So let's find the intensity of the reflected light. Now, different textbooks use many different symbols for this. So for me, for reflected light, I use the symbol I3. And you'll see why in just a moment. So the equation is the intensity of reflected light equals sine squared, difference of the angles, over sine squared, sum of the angles. Oops, that's a little messy. Let me fix that. That's a theta 1. So this is sine squared 30 degrees minus theta 2, which was 19.5, all over sine squared 30 plus 19.5. The difference of the angles is 10.5. The sum of the angles is 49.5. So this is approximately sine of 10.5. Take that result and square it. You get 0.0332. Divided by the denominator is 0.578. This equals 0.0574. That's the intensity of the light. If you want a better grasp of the meaning of this value, multiply this decimal by 100 to convert it to a percentage, which gives 5.74%. Last part of the calculation. Well, we know the light gets split into two different portions. Again, the refracted or the bent portion and the reflected. So let's find the transmitted light's intensity. So the light that gets transmitted, that passes through the substance, gets refracted. I call this I2. So it should be I1 minus I3. Initially, before the light strikes the glass, you have 100% of it, or 1.00. And then we subtract away 0.0574, giving 0.9426. Again, multiply the decimal by 100 to express it as a percentage. This is about 94.26, or you could say 94.3%. Perfect. Now let's just check our calculations. Google FET simulation, bending lights, and you can obtain this simulation here with a laser pointer. Press the laser pointer on, use the protractor, and here we see the theta 1 of 30 degrees. Here we're in air, and then this blue portion of the screen represents glass. And here's the 19.5 degrees, the angle theta 2, once the light enters the glass. And just as we predicted, we get that smaller angle inside the glass as the light bends closer to the vertical axis. Before the light gets split, notice how it has 100% intensity, I1. Here's the transmitted, bent, or refracted light, I2. Now it's a little different than what we calculated, just rounding errors that accumulate with all those decimals. And here's the reflected light, same as we calculated. So notice how the simulation even shows the reflected light as very dim. It has a very low intensity. So that's how you apply Snell's law and calculate the intensity of light.